Okay, so in this chapter, we will focus on the mathematical description for flow. So as he said in the video, looking at the vector fields, there were two main pieces he looked at. He looked at the rotation in those vector fields, and then he looked at the length of those vectors. So was the flow faster in some places, slower in other places? There are a few different examples that we're going to look at for this flow. First one is going to be the airflow, so like the wind. We also could look at the flow of fluid. So that was what we saw in the video. And then the other main application of vector fields is electromagnetic fields. So we're going to start out with the definition of a vector field. We're going to look at some sketching and then some applications. Okay, so a vector field, the general notation is that it's f of xy, so it's a vector, where the first component is a function of x and y. We normally use p. Second component is also a function of x and y. What this is saying is that at each point xy, there is a vector that depends on x and y. This also expands to 3 space as well, so there will be vector fields in 3 space also. So first example, our vector field is simply going to be xi. So we're going to sketch that. Okay, so the first thing that you should notice is that this vector field, all the vectors depend on x but not on y. So at any given x, all the vectors will be the same. At x equals 0, you just get a point. When x equals 1, you get the vector 1, 0. So that would be a vector like this. Likewise, when x is negative 1, you get the vector negative 1, 0. So that's something like this. So you need to pay attention to both direction and magnitude. So in the video, he said a lot of times we make all the vectors the same length. I don't do it that way, so I want you guys to have vectors that have the correct length. If we go to x equals 2, so right here, let's do 3 instead. We're going to skip that one. So at 3, we have a vector of length 3. Do you guys get the idea? Now would be a good time to answer. Okay, great. I believe when you did this in calc, you were told exactly how many to draw. Does that sound right? Or you were given a certain area? Okay, I won't do that. So do you see that some of them are going to overlap? Like if I started at 2, it would go all the way out to here and overlap. I don't like them to overlap. So I'm never going to tell you a certain amount to put in. You need to get just the general idea. I really strongly prefer, though, that they don't overlap. So I at least want the right direction, the right magnitude, and then not to overlap, but enough that I understand what's going on. So you should see a few different patterns. You should understand that no matter what value of y is for any given x, all the vectors will be the same. And you should see that as you move away from the origin, the vectors have a bigger magnitude. Okay, same is going to be true in 3-space. If you were to draw these in 3-space, we're not going to draw them by hand in 3-space, but in your homework, you'll have to pick the correct vector field. What does this remind you of from calc? Slope fields. Yeah. So we're going to draw one more before we move on. So this one is going to be a little trickier. Okay, in my opinion, it's easier to start along the axis. So at the origin, that's just the vector 0. At this point here, 0, 1, we get the vector 1, 0. So that'll be like that. At this point, 0, 2 will be the vector 2, 0. We'll go to 3, 0, etc. Likewise here, 0, negative 1 will be negative 1, 0. And then negative 2, 0, and negative 3, 0. So those are along that axis. We also might choose to go along this axis as well. So 1, 0 would give us 0, 1. So right here. This one would give us 0, 2, 0, 3. Here, negative 1, 0 will give us 0, negative 1. Okay, with me so far? Okay, the next ones that'll be nicer to draw are at all the points along the line y equals x. So if I look at the point 1, 1, that'll give me 1, 1. If I look at 2, 2, it'll give me 2, 2 again. So that's those. And then we have to fill in, oh, sorry, we should go along this way also. At this point here, we have negative 1, 1. So it'll be 1, negative 1, just like that. And then it's going to go something like that. Again, they don't all have to be perfectly placed. You just have to get the right idea across to me. And then we need a few others. We should pick a few points here, pick a few points on all sides and see what's happening. Well, here I guess we kind of handled those already. Let's choose this point. So this is 2, negative 1, which means we would get negative 1, 2. Something like this. And likewise, you would see them continue to do that. If you plugged in some points over here, you would find them following along these vectors. Same thing over here. Are you guys comfortable with being able to do that on your own? Yeah. Okay. Do we get the gist of drawing a vector field? Yeah. Okay, so that's the stuff that I was saying the other day isn't really new to you. The rest of this stuff is new, but this you guys have done before, just under a different name. You do need to know the other notations or other ways that you might see a vector field written. You might see that. You might see f of xy. You might see f of xyz. Or, if we associate x and y with a radius vector, you will see F of R. I would say the ones on the left are more common. So F of R, you're not going to see a whole heck of a lot. But now you have it just in case. Okay. Next example has to do with inverse square fields. Inverse square fields relate to Newton's law of gravitation. Have you all used that law before? Have you seen that? Does it sound familiar? Yeah. Okay, great. That's Newton's law of gravitation. Do we know what this says? Like, can someone put that in words? Is this something you've done, but it's been a while? Okay. So this says that particles that have masses little m and big M are going to attract each other with a force the magnitude of F. Okay, so the force that is exerted by the particle with a mass of big M to a particle of mass little m is in the direction of a unit vector. Okay. Before I write what that is, I want us to draw a picture. Let's say that we have the origin here. Scratch that. Let's say we have the mass, the particle that has the largest mass is there. I'm going to place it at the origin just for convenience. Then we have this particle that has a mass of little m. The distance between them we're going to call r. Big G is the gravitational constant. So our direction then, this vector here, is going to be the opposite of r over the magnitude of r to make it a unit vector. So F of r then is equal to this, so that m times big M times G over r squared. And then we have to throw a direction in there. So that's r over the magnitude of r. With that negative, though, normally gets put out in front. This is called a gravitational field. So I think that's going to come up in your homework when you see it. That's what it's talking about. This is a gravitational field. Generally, though, this is the way it's written. This is all a constant. Sorry, that should be a vector. So normally it's written as c over the magnitude of r cubed times r. So those are the same, just written differently. But in your homework, when you see inverse square fields or a gravitational field, this is what it's talking about. Next thing I want to talk about is what's called a gradient field. Okay, hopefully we can recall the gradient. Do you remember what the symbol for a gradient is? Upside down triangle or delta. If we take the gradient of some function f of xy, what does the gradient tell us to do? Both partials, yeah. So we take the partial with respect to x, multiply it by I, partial with respect to y, multiply it by j. Okay, so then the gradient is really a vector field. In 2 space. You can also do it in 3 space. And this is called a gradient vector field. Sometimes it's just called a gradient field. Sometimes it's called a gradient vector field. So we are going to sketch the gradient field of the following function. Okay, so our gradient is 2x comma 2y. Okay. If we start at this point, 0, 1, that will give us 0, 2. If we start at this point, 1, 0, that'll give us 2, 0. Likewise on all of these. If we go to the point 1, 1, it'll give us 2, 2. Same thing up over here. So do you see what I'm doing? Okay. Here's what's important for this one. Do you see how they all start at this circle right here? Okay. So that circle is a level curve. Specifically, that's the level curve where phi is 1. That level curve is not part of your gradient field, but it's interesting to know. So the same thing is going to happen. If you were to start at this point, you would get much longer vectors in the gradient field. Again, those would originate from some circle. And that circle will also be a level curve. Okay, there's more that's important to this gradient field besides just drawing the different vectors. One thing for you to know is at each point, the vector points in the direction, what direction? It's not just some random direction. Think about the gradient. Gradient points into the direction of what? Maximum increase. So at each point, the vector points in the direction of max increase. And a few things for us to notice. First one is that the gradient vectors are long. Where the level curves are close to each other. There's a reason for that. This is because the length of the gradient vector is equal to the value of what? Length of gradient vector is equal to the value of what? What is the gradient related to? Okay, yes. Not what I'm looking for, but yes. When we were looking at the rate of change in a certain direction, how did we find that? So how is z changing at a given point for x and y? So remember we talked about we can look along the x-axis, along the y-axis, but what happens if we're talking about some other random direction? What did we calculate? It's 2 words. Both words start with a D. There we go, directional derivative. So length of the gradient vector is equal to the value of the directional derivative. So if you have level curves that are close together, that's a steeper graph. Okay. One last thing to talk about. We say that a vector field F, big F, is conservative in a region if it is the gradient field for some function little f in that region. Okay, so here's what that's saying. If our big F is the gradient of some function, then we say that big F is conservative. That little f is called a potential function. Of big F. So let's consider the vector field with components 2x and y. I want to know, is this vector field conservative? In order for it to be conservative, it has to have some potential function f. Okay. Is there some function that when I take the partial with respect to x, I get 2x? What's that going to have in it then? X squared. It also needs to be the case that when I take the derivative with respect to y, I get just plain old y. 1/2 y squared. Okay, so then check the gradient of f. Take the derivative with respect to x, we get 2x. Derivative with respect to y, we get y. So yes, we would say that f is conservative. Okay, at this point, it is not my expectation that you can come up with the potential function. This one was one that wasn't too bad, but sometimes they get much tougher. What we will be doing this section is I will be giving you the potential function, and then you will prove that big F is conservative. This is not very important for this section, but for the rest of the chapter, the idea of conservative is important.